Optimize. A Journey Through Database Query Optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
No, the idea is like, to expose you, like here, that Calcite is the state of the art, is the only sort of open source standalone query optimizer as a service. There's Orca, which we'll talk about today, but like that's now closed source, right? Like that's the best. So if you're unhappy with the best, let's make a better one, right? Okay. All right. A lot to discuss today. Actually, today's paper was a pretty brief and pithy in terms of what they're explaining. So I'll go a little bit more background based on sort of jumping ahead to what we'll see in Orca, because that paper you guys read is the precursor to Orca. It was written in Erlang. Orca's not in Erlang. They got rid of that. I'll explain why Erlang matters in a second. But like, again, going back to what I said before, like I can read it, I can understand it, I know what they're doing, and I can read them myself. Whereas like the bottom-up stuff is always a bit more convoluted. But we'll come to that later. Okay. All right. So obviously, project 1 is still underway for you guys. I'll talk about project 2 at the end of this class today. For the talks coming up today, we have at 4:30, so in what, hour and a half, two and a half hours, the Germans. Like the Germans are going to be giving a talk with Victor Leis and Thomas Neumann. Thomas, you've read a bunch of the papers. We're going to read his paper next week, next Wednesday. So they're going to give a talk about their proposal to replace SQL with this thing called SANE-IR. It's a SANE replacement for basic relational algebra expressions. It's a intermediate language for going from one sort of SQL-like from one system to another SQL-like another system. So they're going to be talking about that today. That'll be at 4:30. Again, you'll get to see the real Germans live. And you realize I'm not making stuff up how awesome they are. P&L will be next week. Again, they're going to talk about Query Optimizer. There's actually an Oracle talk tomorrow. That'll be at noon for the database group. I can post on Piazza for that once I get the information. And then in 2 weeks, we're going to have a speaker from, I think he's now at Facebook, but he had a startup called Looker that got bought by Google. And as part of that project, they had this thing called Malloy, which is going to be one of these, a replacement for SQL. So like a DSL that they claim is better than SQL, but instead of actually just going directly from their language into something, a physical plane you would execute, which the Germans, I think, and the Germans are doing transpiling too. But what Malloy is going to do is going to take your Malloy query and then convert that into Postgres query, or Postgres SQL, and then run that. And again, instead of replacing the whole the physical representation. Yes?
What's the Oracle talk going to be about?
I don't know. Okay. It might be JSON stuff. I don't know. I mean, just email Larry and figure what he says. No, tomorrow at noon. All right. Again, these are all optional. Again, this is going beyond what we discussed in the course, just to give you exposure to more things other than the papers we read and the topics we discuss in the lectures. All right. So last class, we began the discussion of parallelization of a query optimizer, and we really only focused on solving one problem, or parallelizing one problem of a query optimizer in the context of a bottom-up system, and that was join enumeration, right? Because they're going to argue that the join enumeration part is the most complicated or the most complex subproblem of the overall problem of doing query optimization, and they want to have a parallel version of that search to own that. And then remember that because it's a bottoms-up optimizer, that they sort of have this, again, stratified approach where they have heuristic rules in this first phase where they're just doing a bunch of rewrites to put the query in a form that where the optimizations you want to apply, like a predicate pushdown or converting outer joins to inner joins. And then once they sort of figure out, the optimizer figures out, okay, here's the overall logical plan that I want to go with for this given query, then they would run the bottoms-up join enumeration, figure out the optimal join ordering, and also the physical implementation of those joins at that point. And then there might be an additional round where they have additional heuristics to sort of clean things up. But at that point, again, after the join enumeration, that's the hardest part for them, and they want to spend all their time trying to optimize that, and therefore they want to parallelize that. And the key technique we saw for them to parallelize the join enumeration was to partition the query search space into disjoint subsets based on that join graph where you could have workers do the join ordering enumeration on a portion of the subgraph, and it can run in parallel of other workers doing the same thing on other parts of the joining graph, because they didn't depend on each other. They didn't require to know the output of one as an input to another. So therefore, you could break it up into smaller subproblems, run all that in parallel, and then once you then it was like a pipeline breaker. Once you get the individual parallel responses from all the workers, then you can go into the next phase. Maybe just do 2 table joins, then go to 3 table joins, right? Expand it out as you go along, but you're sort of doing this in waves, right? And again, because the key thing, we'll see this again today, is like you need to know that the parallel tasks are independent, because otherwise then you're just executing in serial order. So again, that was in the context of a bottoms-up search. So now we're switching over to the top-down or transformational search. And the challenge here is that the search complexity is going to be a bit more, it's going to be larger than in a bottoms-up joint enumeration, because again, in a top-down query optimizer, there isn't this stratified search where, I mean, there isn't. Like, you can have heuristics that can apply without doing a cost-based search. But just assume that we're just throwing everything all together into our search space, doing explorations and the transformations, and therefore the complexity of the search problem is much larger, because it's not just trying to solve the join ordering problem. So an example from the Orca guys is to consider this query here, TPCH6, query 6, and it's a pretty simple query. Like, it's not that complicated. We're only doing a 6-way join. And so in this case here, the number of different join orders we consider, they claim is going to be less than 100,000, right? Assuming you're throwing away Cartesian products, maybe you don't look at always, exact copies or the all commutative operations, right? So they would say, all right, if you're just doing join order in a transformative system, transformative query optimizer, then about 100,000 choices you have to consider for the joins. But if you look at all the possible transformations you could apply for this given query, then everything else is going to be roughly 230 million different choices you have to consider. So what they're claiming that is that in a transformational-based system, because you're trying to do everything all within a single unified search model, there's just simply way more choices, and therefore parallelism is going to have a bigger impact and make a bigger deal in this environment. And that's why we want to definitely parallelize our system if we're doing a top-down system, top-down optimizer. So if we go now back to in lecture 5, when we talk about cascades, right? The original cascades paper sort of mentioned that you could kind of do things in parallel, but the original definition, or at least description of how they were proposing to queue tasks and execute them, was through this last in, first out stack, right? So as a transformation rule gets applied, it can generate new tasks or new actions, additional rules to do, additional explorations we want to do, and those are going to just get appended to or put on top of the stack. And then now there's some schedule thread that is picking off whatever's at the top of the stack and executing it, right? So the idea is that this stack is a way to implicitly represent the dependencies between the tasks, because if I'm on the stack and I put my children that I need to know that they complete before I run on that stack, then I put them on top of me, and then the schedule will pick those tasks off, execute them, and then at some point you pop out the stack enough where like that task then gets executed, and at that point it knows all its dependent children have been executed, and therefore it's safe for it to execute. And they argued again in the Cascades paper. I think the Microsoft textbook also mentions this too, that like instead of having the doing of recursive calls by putting everything in this sort of global heap stack, you're less likely to have out-of-memory errors, because now you're not worried about doing like super deep traces down in a stack from functions calling functions, right? But the downside of this, obviously, what in the paper you guys read talks about, is that if you're putting everything in a stack, then you actually lose more detailed information about the dependencies between the different tasks. All you really know is that for a given task that's in the stack, if it's at one level, then it's anything that's going to be dependent on it has to be below it in the stack. But it doesn't say anything about for two different tasks right after another or contiguous tasks, are they dependent? You don't know, right? So let's see what I name of this. Say that we start off doing some task, right? And task is being generically defined. We'll go more detail in a second. But say it's doing an exploration of a group or a group expression, right? So then this task says, okay, well, I'm going to generate a new task, my children tasks. So the first thing you got to do is put yourself back on the stack. This is a way to essentially re-queue yourself and say, all right, I'm going to pause myself now, but I want to execute some point in the future. But there'll be some tasks that I'm going to add in the stack above me, and I can only run when those guys complete. So then it says, all right, I now want to add task 2. It goes ahead and adds task 2, but then now it suspends itself or pauses itself, kills itself, however you want to implement it. And then now task 2 is at the top. It's allowed to start running, so it runs on the worker. And then same thing, it wants to generate new tasks that it wants to execute that it's going to be dependent on. So it puts itself back in the stack, adds task 3 and task 4, goes ahead and kills itself. And now the worker just pick off the things off the stack one by one. So take task 4, run that. Take task 3, run that. And then now task 2 knows that there's nothing above it in the stack, and knows that it's children tasks, right? Like could have been exploring down below its group children, could have been running the implementation rules to convert logical expressions to physical expressions. It doesn't matter. We know that task 3 and 4 are completed, and that's what task 2 required to get finished first. So then task 2 is allowed to start executing, and then when it's done, then task 1 can run, right? Again, it's a simplistic model. It doesn't require really any deep thought about how to schedule things, assuming we have one worker thread. But again, now we're reduced to running on a single CPU core, right? And again, the issue is because it's just the order in which they appear in the stack. That's all we know about the dependency between these things. And what we really want to be able to do is actually track the fine-grained dependencies between them, and so that we know at any given time what is allowed to be run, and is one task allowed to be run in parallel to another task, because they don't require the input or the output of each other. So that's what we're trying to solve today, right? How to do parallel top-down search in this particular model when we have all these tasks are being generated and we need to keep track of who's waiting for what. Okay? And then I'll finish up going over what's expected for project 2. I should say also too, if you have questions as I go along, please stop and interrupt me. Like, don't come and ask questions at the end. If you have questions during the lecture, somebody else might have the same question. So just stop me as we go along, okay? I should have said that at the beginning of the semester, but I say it in the intro class. All right, so in this implementation, what they're going to do is they're going to replace the stack with a more general purpose scheduler that's going to track the state of each task, and it's going to be able to pick them off when they're allowed to run. And the way they're actually going to implement this, the paper doesn't say it, is that within every single group, there's actually going to be their own little mini job queue. We're going to keep track of it. Here's all the tasks that have been suspended. Like, it's sort of what are the portion of this dependency graph we're going to maintain? What portion are those tasks going to be living at a different group, so that we're not just traversing this graph every single time. We can just look within the group and say, what can run actually right now? All right, so again, we'll replace the stack with a scheduler. And once we identify that a task is runnable, meaning it doesn't require the output of any other task, dependent task, to complete before it's allowed to start running, it's going to go ahead and be able to pick it off and assign it to a worker. And the way we're going to keep track of these things is through this dependency graph, where we're going to link the sort of child-parent relationship between, here's some parent task that created a child task, and therefore I need to know, again, its output before I can start running, right? And the guarantee is that, again, we have to provide is that we can allow a parent task to start before its children start, because obviously if a parent's going to create children, it needs to be able to run before the children actually start running, because we don't know about the children yet. So we can allow the parent to start before its children do, but we can't allow a parent to finish before its children do. And in some cases, we could have a parent create a child, the child runs, it completes, then we come back to the parent, and the parent says, okay, thank you for that output, but now I want more children. Right? It's a weird Elon Musk thing, but like it makes more children tasks. It's a terrible person. All right, so it makes more children tasks, and then, but it still has to, if it's going to create more children, it has to wait till they finish before it can finish. And as I said, the paper doesn't say this, because I think it's what, 2007 or 2009, thank you. But this is a precursor to what later on became Orca. Again, This is going to be in Erlang. We'll explain why that matters in a second. Orca is going to be in C++, right? So they threw away the Erlang prototype and switch over to Orca. Or sorry, switch over to C++. But like a lot of the core ideas that they developed in this prototype then ended up in Orca. So we'll see some of these same ideas later on. Yes?
They don't talk at all about the scheduling costs or how the entire scheduling algorithm works.
Nope.
They say we're going to schedule stuff
Nope.
based on these dependencies.
Correct.
And so they also don't mention how they're going to evaluate whether or not some of the dependencies have been completed for a certain task, right? Aren't those things very, like, do they talk about it anywhere else?
So, no, so the Orca paper doesn't talk about it. So my understanding of the way the prototype works is that for like to know where your dependencies are they finished, they're relying on Erlang to do that. Because you would have child processes in Erlang and say, notify me when this actor object thing finishes.
Right, but like if I'm launching 5 things and one of them finishes, I'll have to go and check, hey, are the other 4 done?
It's like a
So
counter.
The implementation details are just missing.
All right, so this is the only paper that exists that I know out there that describes a parallel top-down optimizer, right? It is also 9 pages long,
Yeah.
right?
3 paragraphs are on their actual implementation.
Yeah. Yes, I know. Yes.
I just feel like they can say we write a very good scheduler, like multi-threading scheduler, or a very good thread pool.
Yes. So a couple things. One is in the late 2000s, VLDB and I thought it was VLDB, but maybe Sigma was doing this. They were playing with the idea that instead of people writing 12-page papers, we're going to write 9-page papers, right? And to try to be more concise and then have a quicker turnaround for reviewing. I know VLDB did that. This is a Sigma paper though, so that sort of surprised me. So that's one side. So I think it's from that era, and that's why it's pretty short. The second one is, I think this is also in the industry track at Sigmod. And for better or worse, the industry tracks are typically less scientifically rigorous than the regular research track because one, you're trying to encourage people in industry to talk about what they're doing, right? And then they don't always maybe divulge the secrets of everything they're doing. And oftentimes we'll see in industry papers, the graphs will actually be all normalized numbers. These actually have somewhat real numbers, but although that one graph for that spiral thing that's useless, but like
I don't know, what was the point of that?
Bingo, it looked cool. They say because it's too, whatever, it doesn't matter. That's it. So that's an example where I think it's because it's industry track paper, they allow that in, right? But like I said, this is the only description of a parallel top-down optimizer. The other description was going to be in the Orca paper, but that's literally going to be a half a page, and it doesn't say anything more than what's in this paper. So it is what it is. No, so
It looks like graffiti.
yeah, the spiral graph. So that means also the authors are top people, right? That Florian Voss guy. I think he was at CWI. He was at Greenplum for a long time, and then now he's got a startup called Detametry, where they basically convert Teradata queries into I think SQL Server queries or Postgres queries. So that he's a legit database. And then the second author is Joe Hellerstein, who's like the top database professor at Berkeley, right? He was like one of Stonebraker students, right? So that's why again I think it's an industry track paper.
It's also I feel it's a different era where like you think a lot of things right now takes for granted, but like at that point they're just starting to have like parallel cores and stuff.
No, 2009. No. His statement is that the multi-core era, people started building data systems and being aware of, oh, yeah, but we're not getting faster clock speeds, we're getting more cores. Let's build something that can be multi-threaded or multi-core. That's probably 2005, 2006, right? No, it's again, I think this is an industry track paper, right? And like I said, most people aren't building a query optimizer. Microsoft didn't really have any papers describing how their thing is not even parallel, right? I was able to do Orca, as far as I know, is the only parallel query optimizer that I'm aware of, at least that they publicly talk about. And this is the only paper that describes the top-down one. It's why I picked it. So is it a great paper? Is it the only one? Yeah.
The idea is good.
Yeah, the idea is good. I did spend some time looking in the code to try to figure out what they're actually doing.
In Erlang?
No, not there, like in Orca. I'm like, yeah. And a lot of the stuff, I mean, it's in C++, a lot of it is extracted away. So they have, I mean, trying to think what's useful I got out of that. So some of the things they talk about in the paper do match up with within the code, but they're not maintaining the dependency graph, the sort of explicit data structure the way they describe here, right? It's my understanding is like within every group you sort of have this like here's what I can queue up and run right now, and then you go look in the group and look at that job queue to say what can I actually run, and that's how they're figuring things out. Instead of having a giant dependency graph for everything, which would be huge, they break it up into every group. Yeah. Okay. So this is going to come later in the Orca paper, but I just want to briefly go over this. Right. So these are the 7 task types that they have in Orca, which is again what came after the paper you guys read. And this is basically going to be the same thing as the Microsoft one that we discovered in the textbook or the original Cascade paper, except they have 7 and the Cascade ones have 6. Right. But this is all the stuff we saw before. Like we have the way to explore the expression or the group expression to generate new ones. We have this optimize call where we can just figure out what's the best plan is or subplan within a group or group expression, right? Instead of apply rules, it's transform. I forget where the actual one comes into place, but if you go back to what we had before, like this is the diagram we showed before, right? Instead of optimize inputs, optimize inputs allows you to, it's basically equivalent of those 2 up there. Right? Instead of optimized inputs, they have 1 per group expression, 1 per group, right? So again, what they're building is mapped back to what we talked about before. There isn't, it's a Cascades implementation. The slight path to things is a little bit different, but at a high level, you could apply the same scheduling mechanism with the dependency graph to this. In the same, there's doing it for different tests.
Have a different function for implementation rules and for
yes.
That's just volcano then, right? Isn't it not? So then why would they have the IMP?
Why would they have this?
Yeah, because wouldn't you want to explore all the moves that you can make within the opt?
I think this just iterates over all the expressions and calls this. That's all it is.
No, I mean the one below.
This.
Yeah. Why do we even have that? Like that's not there in.
That's their apply rule, like apply their implementation. That's their apply transform rule.
Yeah.
Oh, I thought that transform is not just apply. Okay, they split it up.
Yeah.
Yes. And the code doesn't say, like, oh, Cascades did this. We're doing it. It's just there's no comment describes this. All right. So as a task is going to execute, all right, as I said, it can generate additional tasks, and that can either fan out, sort of going across the same level and adding more things, and those could run in parallel because you're not required the input of the output of those as your input, or you could traverse down into the search tree, and those would be considered dependent tasks for yourself. So now they're going to define tasks in terms of their goal. Essentially, what is the call of this? What function are they calling from the 7 list I had before, and on what given input? And then the idea is that if now there is a task that is running that is described based on one of these goals, if other tasks start getting queued up and they have the same goal, you're just going to pause them until you wait to find the output of whatever the task it is that's producing this output, right? And they have a mechanism to do that automatically, right? And then once the first task with the same goal finishes, all the other tasks that are waiting for the output can then start up, and then you don't have to pass data between or information between the different tasks. They just immediately go look in the memo table, which is the global state of the search, right? Whether it's a global for the entire tree or it's based on per group, depends on implementation, right? But they would go in the memo table, and that's how they would learn about what was the result of the goal, the other task with the same goal as you, right? So again, because you don't want redundant tasks computing the same thing, like traversing down on the same group expression of the same children, producing the same result, right? because the other rules don't need to know what other rules are running at the same time. Therefore, you do zero coordination. So if other rules are generating the same thing over and over again, this mechanism here prevents you from doing unnecessary calculations. All right, so the search state dependency graph it's a pretty simple state machine. Nothing here should be too exotic for anyone, right? Task starts. The first thing it has to do is it gets created by another task. We mark it as runnable, right? And then once there's a worker available, it's assigned to that worker, then its status changes to running, right? No surprises there. But then as soon as it tries to create tasks where it depends on the output of those tasks, it has to get suspended, and then it's put into this inactive state. And again, that's just put back into a queue for the given group that it's based upon. And then at some point, when it gets notified that all the other tasks that it depends on the output are completed, then it's allowed to switch back to the runnable state, and then it can repeat this process over again. So the same transformation rule, the same task, could get sort of woken up and run multiple times, because every time it run, you're getting more information about what other tasks ran, and then that allows the task to make other decisions about what it wants to do next. And then at some point when it finishes, then it goes in this finalized state, and then it eventually just gets discarded. Now, its state is maintained in the memo table, because you don't want to end up recomputing something that you've already computed. So even though the task context, whatever metadata we're maintaining about, I'm doing this task at this time for this thing, all that gets thrown away, but the result of its computation or calculation, that persists in the memo table for the life of the query, at least in the optimization phase. So that way you don't end up queuing and running things again. So if we go back to that example before, we had sort of a one task generating a series of other tasks, right? So the very beginning, we just have task 1. It starts running. It's going to create a new task, task 2. This gets marked as runnable. But then task 1 immediately has to get suspended, and then it marks itself as inactive. And at which point, some worker could pick up task 2. Its status changes as running. That prevents another worker from trying to pick it up and running at the same time. And then it creates task 3, task 4. These are both marked as runnable. Task 2 has to get suspended. It goes to inactive. And then now the other workers can pick up 3 and 4. When 3 is finished, it goes to the finalized state. 2 can't still run because it's waiting the output of task 4. Once that's complete, then it completes. Task 2 can run. It finishes, and then task 1 can run. So the key thing, and I sort of mentioned this, but I'll be more explicit and say that the tasks have to be implemented using a reentrant protocol, meaning like we have to have the ability to pause the task no matter where it's at when it says, okay, I need these output, right? The task gets paused, and then when it resumes again, it has to pick up exactly where it left off when it was paused. So this is different than idempotent. Idempotent just means that if I run the same thing over and over again, I'm going to get the same result. Reentrant basically says there's some internal state where I'm keeping track of, like, where did I stop the last time I ran? So when I run this task again, I'm not starting from the beginning. I'm starting wherever it is that I left off. Because again, now you can think of like a task having a for loop where it's generating inside the loop, it's generating a bunch of more tasks, and you maybe generate the first batch, and then you want to wait to see what happens to that first batch before you go maybe generate the next batch, right? Because you don't want to flood the search space with a bunch of tasks all at once, because then you're just doing volcano. Maybe do a little bit, see what happens, and then now you can make decisions about what you're going to put out in the next batch, right? Because the promises could change, and other things could change as well, right? So again, we need to implement this as being reentrant. When I looked at the Orca code, it's just an internal state machine where they have these blocks like, okay, I'm doing this, and if you come back, you know where to jump into where you left off. I think Python yield is basically the same idea. If you build it if you have an iterator, where Python is doing that for you automatically through the yield function. For this one, if it's in C++, you have to implement it yourself. And then Erlang, I think Erlang gives you this for free too as well, and that's why they did it. All right, so let's look at a simple example. So this is come from Orca. And the ordering is a bit weird because the Orca paper doesn't really describe what they're doing. And again, try to trace through the code and understand how it goes. So this is my understanding of how these parallel tasks are getting executed and what happens. So at the very beginning, you call the optimize function on the group at the top. And request is, I think, is just saying for the invocation of this query, run my optimizer. So the first thing they're going to call is implement group, where it's going to go say, okay, well, go figure out how to actually pick the physical expressions for this group expression. But at this point, you don't have any of those. So then you got to do, so you call explore group. So then you get out now for my given output, start firing off rules that generate equivalent logical expressions for my output. But at this point, we don't have any of those. So we generate sort of we do explore expression on the null set of the output, which then just converts the output into the most basic logical expression. So now we get a result like that. So now we at least have one logical expression we start doing something with. So now we could go down and start doing exploration rules from the transform functions, and that could generate different permutations of the logical expression that we have so far. Alternatively, I could then also start exploring down the children and make an explore children call down and go now recursing down into below me, start looking at additional groups down below, right? So at this point here, these things could be at sort of this level of the tree. These could all run in parallel because this is just applying transformation rules. It doesn't require the output of another one or any other task. Likewise, I could explore down into the children. That's fine. I can run that in parallel. Meanwhile, I'm just generating more logical expressions up here, right? So within one level of the tree, all these things can run in parallel. So assume this guy's going down, doing whatever exploration at once. That's fine. Then coming back up here, we could now that we have some logical expressions, we can start running the implement calls on them to generate the physical expressions for any expression that we have, right? So now we call more transformation rules, which then fire out the implementation rules, then start generating the physical expressions here. Now in this case here, if we want to start costing them, which I don't think happens in this pass over here, that happens in the optimized pass, which is sort of subpart of the tree. At this point here, if I want to start costing, I'm going to have a block when I go down into my group below when I say for AB hash join on CD, since I need to know what's the physical cost of actually joining AB below me, then that could block have dependency on anything that goes down below here. So I think this is just to do exploration, as like I said, without any costing. And then there's this other optimized group expression call that they make, where that's actually now trying to look at, okay, for the physical expressions that I've generated during these implement calls, start then computing the cost of them. And like I said, these are going to be recursive calls because I need to go to my children, right? So G0 has got to go to group G0 has to go to group G1 and say, okay, what's your best physical plan or physical expression to do whatever it is that I'm asking you to do? And so in this case here, this would be a blocking call for the first one here when you go down, because you have to wait until some task down below produces this result for you. So again, we can't do recursive calls. This thing's going to get blocked, waiting for the output of this to finally arrive, and then it can then percolate that cost going up. And again, this is happening. Actually, I think Orca is doing accumulated cost bounding, not predicted cost. With accumulated cost, it's obvious, right? Because then you just say, okay, as I'm looking, so maybe like where there's forking here, I would know I could cut things off because I know I don't want to explore stuff. But it mostly makes sense when you on this side over here when you start fanning things out. So what you can do the predicted cost bounding when you fan out within a given level. The accumulated cost bounding when you fan out a different level. Predicted cost would do the same thing, but you could just avoid having to go down and fan out even further. At a high level, this is clear.
For the predicted cost, like when you're expanding like sort of similar to what you were doing with export here, you're doing but like when you're doing predicted cost, you sort of know based on the logical thing here, but like also you could potentially like in the serial case, you sort of could down the optimization of the right-hand side, say in a join, to be the cost of the operator plus like whatever the left side.
So if you're doing predicted cost, like maybe the question is, if you're doing accumulated cost would allow you to hack these things off, right? Where does predicted cost come in? So my understanding is that it's when you explore the group expressions, right? I'm only showing one line from one group to group expression, but you can imagine this thing would fan out too, right? So now when I say, all right, here's all my group expressions that I have, they're all logically equivalent, right? AB join CD, A join BCD. Now I want to say, all right, which one of them do I predict is going to have the most benefit for me? And therefore, only do the transformation rules for those, right? So you would do the cutoff for predicted cost would happen over this side here. And then now if you go down this path, say optimize children to get actually the physical cost of things, you would, since this thing's not going to do a bunch of implementation rules, you would just look at whatever you have and say, okay, this is the best one that I've seen.
So they limit the number of children that they are storing as explored. And in that case, they're marking it as explored, but they haven't actually explored all of them.
Wait, hold on. Sorry, say it again.
So they're limiting how many.
In predicted cost.
Yes, using predicted cost.
So you look at the group expressions, right? So the logical expressions, right? I guess you may not be able to generate all of them until you run all of these. Let me think about the statement.
I'm pretty sure you generate all of them, but then you order them.
You generate all of them and you order them, but you could, independent of the predicted cost, you could limit to say how many you want to, you're like in the first wave,
right,
how many we're going to generate right now, and then pick which one has the lowest predicted cost. And then when you come back, when this task would executed, this task gets executed again, you could then say, okay, for the expressions I do have, maybe look at the next 10 things, right? And apply 10 transformation rules for them.
So the predicted cost for guidance.
Yes.
And they use this heavily.
No, Orca I don't think doesn't do it. It's only cumulative cost. Please, I'll check the code again.
So where did the predicted cost idea?
I'm just trying to say, like, even though the paper doesn't talk about predicted cost, cumulative cost, we read that in another paper. I'm trying to say how we apply the concepts from other papers to what they're trying to do here, right? I'm just trying to point out that, like, the accumulated cost happens over here. Over here, if you're just dealing with the logical expressions, you don't have a physical cost, but this is where you could use the predicted cost to like start truncating things.
Yeah, that's
Okay.
And you would order them, right? Like that's the promise concept.
Yeah, I'm not sure the promise here, but you would.
What are the way you would tackle them? Like when you're doing the opt over there, which groups you would optimize first in the inputs would be dependent on the promise of the moves that you have, that you've made to create those expressions.
Within one group or within the global?
So within a group, you create these expressions,
yes,
right? And you order the ones which you want to actually, whose children you want to optimize first.
Yes.
Based on promise.
Yes. Yes. So is that clear to everyone? So like, I'm not showing the promises here, but every single time you have these these different choices of rules you could apply, they attach to them is going to be a promise. Say, I think I'm going to be this one, provide this amount of benefit for you. And again, it's an arbitrary number. It's just a weight to say this. We think this rule is going to matter more than others, right? It's a relative thing. So now I'm only showing in 2 here with ... But like there could be hundreds of rules I can apply. But then I'm going to use the promises and maybe pick the first 10, right? Apply those transformations, and now that's going to generate a much more logical expression for me within my group. So this column here will get expanded. And then now when I want to go now start doing exploration, I could use if I'm doing predicted cost bounding, I could decide, okay, I'm not going to go down and start looking at the implementation rules for a given group expression if I don't think it's going to be a big win for me, right? Because this is trying to convert the logical expressions into physical expressions. So I predict how much benefit, how much work I might have to do, like based on the number of tuples going to come out of the join, and then I could cut off the ones that will be too costly. Yeah, I showed you on errors. I'm just trying to show how you apply promises and apply the logical cost bounding and the physical cost bounding in the context of all the same search tree. They just happen in different locations. All right. So there's two graphs that are interesting in this paper. The first is identifying, okay, well, if you build a parallel optimizer, how much can you actually parallelize, right? And so the first experiment they take two synthetic queries, a star schema query and a chain query or a linear query, and they're going to run run their optimizer prototype, and at every single step along the way, they're going to look at all the queues that are inside the system and say, how many tasks are available to run right now in total? And then how many tasks could actually be run in parallel with each other? And the idea is the goal would be the smaller that gap is, the better off you're off because there's more tasks. You don't have to run things in serial order. So what they point out, and it's kind of hard to see in the graph here, but the very, very beginning on both of them, that it's basically a sequential execution because you have to sort of build out the first pass of the tree, figure out a bunch of the tasks that we would execute in parallel. You sort of have to get to the bottom and build an initial query plan first, right? So there's always this initial phase where there isn't a lot of parallelism to be achieved, but then once you sort of flesh out the overall query plan, then the floor opens up, the room opens up, and now there's almost 90 to 85% of the tasks that are available could run in parallel. So this is good, right? This is matches our expectation that in a transformation-based query optimizer, a top-down query optimizer, since we're throwing everything in the mix, a lot of these tasks can be run are independent of each other and therefore can run in parallel. So that's good. But then what kind of speed up you're getting? Well, first of all, the downside is that this is 2009, so they're running this on a 4-core desktop machine, right? Your cell phone at this point might be more powerful than this. So what they're going to do is, for both of those two queries, again, they're going to scale up the number of cores that the optimizer is allowed to use to do the parallel search, and then you want to see what the speed up is going to be. And again, the goal would be in a perfectly scalable system that if I double the number of cores, then the search speed, or sorry, the optimization time should get cut in half, right? I should have a linear speed up. And what you see in the case of the star query for the, as expected, because there's just going back here again, there's just way more parallelism opportunities than for the chain query here, right? That for the higher number of tables you're joining, so go from 2, 4, 6, 8, 10 tables you want to join with, as you add more tables to join, therefore just more tasks and the more things you have to consider, and therefore there's more parallelism opportunities. In the case of a 2-table query, you see that the performance doesn't do that great after going beyond 2 cores because there's just the amount of independent tasks to deal with those, just joining 2 tables goes down quite a bit. And it actually gets worse because of the overhead of the coordination between the different threads. Everyone is writing to the same memo tables. There's last contention and so forth, right? So in the case of the chain query, the same issue. It doesn't get the same kind of scalability as you get in the star query, because again, the chain query basically specifies that here's a specific order I have to have for when I join things, and again, that limits the parallelism opportunities. So the other thing, the main takeaway from this graph also, as I already said, is like we're gonna have to apply the same techniques we do in actually building a new system to build a scalable, multi-threaded data structures from the internals of the query optimizer. That's going to matter a lot when you start running things in parallel. All right, quick show of hands. Who here has ever written in Erlang? Nobody. Who here has never heard of Erlang before this paper? Some of you. You went to CMU. This is like PO heaven.
No, the CMU is like SML.
Okay. Is Erlang considered verboten? I'm looking at you because you hang out with those guys. Because it's useful. Yeah, okay. All right, so Erlang is a functional programming language from the 1980s based on message passing actors, although I think it was, they don't describe it in terms of actors. It's like message passing objects, but it's basically the actor model, right? And this was developed by Ericsson in the 1980s. It's actually a fascinating thing because like they were trying to scale up, build scalable systems to handle all the telecommunications infrastructure they had to build. And so they built their own query language and their own programming language and their own runtime that is based around these sort of core principles of like, here's how to, instead of everyone re-implementing the same sort of functionality and features you'd want to build a scalable system, let's all just build that as first-class concepts in the language itself. And then everyone gets these for free. So out of the box, you get fault tolerance, meaning like if one, what they call process fails, you'll get a message, but then it can get fired up again automatically for you. They can do hot swapping. So like I can have the code actually running and I can replace, like do live updates on the code while it's still running, replace other actors without having to take the whole thing down. And then everything's being implemented through what are called green threads. They're basically, they're like fibers, sort of like they're managed threads within the language runtime itself. So say what you want about functional programming languages. Whether or not you should build an entire system on it, that's a whole other story. But of all the functional programming languages that are out there, this is the most common one, the most used one most commonly used one that's to build a full entire database management system. So probably the most famous one is actually SimpleDB from Amazon, which is before Dynamo. They had this thing called Simple. It's a key value store that was like meant to be a fast path to store small files. Instead of doing S3, you would use SimpleDB. I think that's written entirely in Erlang. Couchbase is a fork of CouchDB. They use Erlang for like the clustering, the distributed infrastructure. React was a key value store based on like consistent hashing, like the rings, similar to like sort of Cassandra. That was written entirely in Erlang. This company failed in 2014, 15. But now this actually runs all of the NHS in the UK. Like their entire the web services are based on React, which is the dead thing. So there's one guy in the UK that basically still maintains it. Anyway, so if you think, all right, this is fantastic, Erlang is a big deal because it's the most used functional programming language to build database systems. Hold your horses. When you look at the full list, right? I only know of 13 databases built in Erlang, and you just see the list of all the other languages. There's more Python, there's more JavaScript databases than Erlang databases. So keep that in mind.
Could you tell what happened to Orca? Like how did it die?
Question: what happened to Orca? Greenplum started in 2007, 6 as a fork of Postgres. They got bought by EMC. And then that was maybe 2011, 2010. And then VMware bought SQL Fire. They bought some other database companies, right? And then EMC is like, wait a minute, we're a hardware company. What are we doing? Why do we have a database? VMware's like, hey, we're a VM company. Why do we have databases? So then they took Greenplum out of EMC and Gemfire out of SQL Fire out of VMware. They mashed the two together. They made a new company called Pivotal, right? So then Pivotal was this sort of a standalone company, and then they made Greenplum open source. They made Orca open source. They had another system called Hawk with a Q. That was like SQL on top of Hadoop. That was open source. I mean, Orca was built as the query optimizer to work on both Greenplum and Hawk. So instead of having to build a query optimizer for both, they built one standalone service that could handle both. Right? That's a good idea. So then Pivotal got bought back by VMware, and then VMware got bought by Broadcom 2 years ago, and then Broadcom basically just they all the things that are open source are now closed source. So the source code, like it's marked as archived on GitHub, it's still there.
I mean, clearly Orca is like the most, other than Calcite, the most successful company.
We are getting ahead of ourselves here. We'll talk about Calcite and Orca like in the context of the market later on. His statement is, second to Calcite, Orca is the most famous or most successful
attempt at creating
What's your definition of successful?
It actually does cascade instead of Orca.
Okay.
That's full.
I thought you were going to mean most widely used. Like it's
definitely not most.
nobody uses it.
Nobody uses it.
I've never met anybody that's like even tried Orca.
But the approach is sane and good.
I say the approach is sane is good. Again, we'll get to that later on. Like, Calcite is the de facto standard. If you need a query optimizer as a service, Calcite's the only game in town right at this point, right? And the fact that it's in Java causes some problems, you know, and it's very opinionated how to do certain things, right?
I think we all know the problem with Calcite at this point.
Yes. Okay. Let's keep going. Well, we're almost done. All right. So, as I said at the beginning, like top-down optimizers, again, because you're kind of throwing everything in the bathtub, all these transformation rules. To me, this means that that's a better target and a better environment for parallel search because because there's so many different things you can consider. If you keep track of the dependencies between the different tasks, then you just let the scheduler figure out what the right way to execute things. And obviously, the quality of the query plan you're going to generate is going to depend a lot on these little mini decisions you're making as you go along the way. Like, if I have a bunch of tasks, which one should actually run first if they're all parallel? Like the promises try to provide those guides. Like, it's not just say, hey, can I have a way to say, they're all can run in parallel? Because as we showed in the beginning, there could be thousands and thousands of tasks you could run at the same time, and you need to be intelligent in how you're going to pick them. The counter argument to today's class would be that, well, of course you need a parallel search if you're doing top-down, because you're kind of just stupidly throwing everything in the optimizer search space, and therefore you have to run in parallel to get anything good out of it, right? And that the better way to actually implement this would be don't do top-down, do the stratified search, do the bottoms-up search, because then you can have instead of having a sort of general purpose search engine try to apply these different transformation rules and figure out what actually you should be doing. If you are the database developer, the person actually building the system, you know what in the order that certain things will be applied because you can apply that domain knowledge of you actually building the system. And therefore, you don't need parallel search if you just do things more efficiently. And so it's not just me saying this. This is coming from the German, Thomas, right? Because I asked him, hey, I'm pretty sure Hypera and Umbra is single-threaded. Is that true? Yes, they're single-threaded because he says that the DP algorithm has exponential worst-case complexity, and therefore, if you switch to a multi-threaded system, you're reducing the problem size by just a small constant. Like maybe you can do 3 or 4 more relations, like bump up that threshold of when you go from small to medium in his paper. And that all the additional complexity you have to deal with now building a multi-threaded system isn't actually worth it. So my counter to this counter would be, if again you're building a standalone optimizer service, you still want to be efficient, but now you're not worried about so much about like, all right, I'm taking threads away that I could be actually using to execute query, because Umbra and Hyper are going to run your queries in parallel very, very efficiently. But now if I'm not worried about running the queries in some my optimizer because it's a standalone piece, then maybe I do want to do the parallel search because I have the resources to use for it. Okay? Yes.
I don't understand your initial argument about why we should do bottoms up. Why, so the throw it all in is bad, but if you do bottom up, you have some domain knowledge. What domain knowledge are you referring to?
The order in which you're doing the steps of the optimization. So the stratified search. Do the predicate pushdown stuff first. Do whatever. Do the unnesting. We'll see next class. Then do the Joman enumeration. Because now the problem is scoped down to, as I said, just maybe 100,000 choices I had to make, which is still a lot potentially, rather than what are the 230 million. And so the top-down people say, okay, well, yeah, we know this is a problem, so this is why the promises can help to sort of guide us to that we're not looking at all 230 million all at once. Okay. Next class, we're going to read an updated version of a paper that the German wrote in 2015. So this is the 2025 version of it, of how to do arbitrary unnesting. So remember there was that subsection in chapter 4 I had you guys not read on like how to do unnesting, because I said the Germans have the right way to do it. So that's what we're going to cover next class. So this is the updated version of where he fixes a bunch of the problems in the corner cases that the original paper doesn't handle. So we'll go over that. I'll briefly also talk about like, here's what Oracle does and SQL Server, the old SQL Server does, and another system where they basically had a bunch of heuristics and rules of pattern matching for looking for subqueries in a certain way, and then try to apply the transformation to then convert them into from instead of nested queries into joins. But the German approach you're going to read can handle anything. And in my opinion, this is the right way to do that. And we haven't really thought through how to actually do this in a top-down optimizer yet. So they're going to do it in the context of a bottom-up. And I think maybe we have to do this one in a bottom-up manner. Okay? So this is a great paper. There's another paper that's also an optional list. If you like math, he proves the bounds of this thing. And you also notice it's a single author paper. That's how he's a freak, right? Like he not only implemented the optimizer to do the thing he needed to do, then he wrote the paper by himself. And he's got 3 kids. All right. Project 2. Okay. So the final project for this course, the website's not up yet. I'll put that up later tonight after class. But the goal is for you to build some project, something based on the topics we've discussed throughout the semester and what we've discussed so far and what we're talking about going forward. And the idea is that you want to get in a small group, at most 3 people, pick some topic you think is super interesting, and then propose something about what you actually want to build. So the deliverable is going to be, there'll be a project proposal on the first Monday after spring break, so March 10th. And then a month later, you'll do an in-class update. It's a 5-minute presentation I'll talk about in a second. Like, here's what we've done so far. And then we don't know when the final exam is yet, but instead of the final exam date will be, you come and do like a 10-minute presentation about here's all the code we built, right? And then we can vote for whoever has the best presentation, and then the winner will get a signed copy of Larry Ellison's biography or something. It's signed by me, so it's not real, right? All right. So again, March 10th will be the first proposal, and the idea is that you want to pitch what you're going to do to the class, and the idea is that you actually want to have thought about what you're actually going to build, right? So you got to think about how you're actually going to implement whatever you want to implement, how you're going to test to see whether your thing is actually correct or not, how you're going to benchmark it, what workloads you're going to use to evaluate it. Again, that's why I prompt you those things in the reading synopsis, right? So this is, again, just to get the ball rolling, get everyone to understand what you're trying to do, get feedback from myself, the WAN, and the classmates. And then later in April, again, this will be a status update. And the idea here is that you're reporting to the class like, hey, we've worked on this for about a month. This is not going well. We got to change ideas. Or, hey, this is going even better than we thought. Look how much great progress we're doing. And then, just if there's anything that surprised you, like, Calcite not being useful or helpful is not a good surprise at this point, or at least, surprise at the status update. But it would be things like that, like, oh, we thought this would be easy because there was this library they claimed they're going to do what we needed, and it turns out it was a nightmare. It's things like that. When you turn in the final report, it'll be basically a design document, and I'll provide a template for this, right? So like, here's what you build, here's how it works, here's why you made certain decisions or why you did certain things in your implementation, how you test this thing, right? What unit tests, what fuzzing tests, whatever you're going to do to actually make sure your thing actually works. How does it work? What are some of the trade-offs, potential problems someone might have if they actually use your implementation? So we're going to make everything open source. We put out if you've seen the other 721 or old 789 courses, there's always a showcase page where here's all the project presentations and the source code for everyone's projects. So people sometimes pick those things up and actually try to run it. So just writing out what people might problems they might hit in the future. And then if you had more time, either for a master's capstone or a thesis, or as a side project, if you want to do more on the project, what would you actually do? And then, like I said, instead of doing a final exam on the day of the scheduled final exam, there'll be a 10-minute presentation. Depending on the time, we either get bagels or pizza, wherever it's going to be. And then we'll come and talk about everything you've done. And then if you can benchmark yourself against something or give a demo, that's always super cool. Okay? Again, this will all be on the website. And I'll provide templates for, not the presentations, but for like any of the design documents, any reports. There'll be a markdown template. You just use that. Okay? All right, for the topics. So we are building a new Cascades optimizer here at CMU. It was originally written by another master student, and then we've been trying to expand upon it for a couple semesters now. But we decided beginning of this year, so about a month ago, to throw it all away and start from scratch. So unfortunately, it's not at the point where people can actually start playing with it. But the way we're sort of thinking about this is like some of the project ideas would be prototypes that are in the periphery of this opt-D thing that we're building. And depending on if you're doing like MCDS capstone or want to do a master's thesis or things like that, like the idea would be build it with in mind that we want to be able to integrate it in opt-D at some later point, get through the semester, get a good grade and all that stuff. And then if you come back in the fall, or we could hand it off to another student who could then take your project and then do the integration, right? So this is a non-exhaustive list of different projects that I've sort of been thinking about, and the opt-D team and when I've been thinking about. So again, this is not, don't think of this as like these are the only things you can possibly pick. If you're doing research in some other area, and you say, hey, this cool technique that we're using in, I don't know, in theory, you want to apply it, or algorithms, you want to apply to the optimizer world, by all means, I'm open to it, right? So don't feel like this is the final list of what you got to pick. So I'm going to go quickly at a high level what these all are. So the first one is building infrastructure to allow us to learn what these promises actually should be. Right? It's been kind of vague. Oh, the developer can decide how to choose, how to pick the right promise for certain things. But how do you know whether it's right? If you pick a static number in there, is that going to be a good thing for any possible query? And so it'd be interesting to explore whether this is done in calcite or a simple prototype, if we can learn for a certain class or category of tasks or rules, like which ones seem to provide the most benefit. So assume everyone starts with the promises 0, but then as you basically iterate and try out different promise combinations, try to retain knowledge or learn from that exploration what is actually the best ordering. And then can go even crazier and start saying things like, is there a way to look at patterns of the query when it shows up to identify what set of promises might be the right thing for it? Like if I have 3 tables in my join versus 10 tables in my join, should the promises actually be dynamically shifted based on that? And this could just be for the initial promises, but then could be a technique to say, as I'm doing the transformations, the promises can dynamically update themselves based on what I see as I go along. As I said just a moment ago, we're going to read the paper on arbitrary nesting from the Germans. That's going to be a bottoms-up approach. How to then write that into the context of a transformation rule in a cascade-style query optimizer, that would be definitely worth pursuing. As far as I know, I think Databricks, my former student is at Databricks, I think she said she implemented this in their Catalyst query optimizer, but she didn't implement all the things you needed to do. So I think it can be done, I think. But the only one that I know that actually maybe has tried to fully implement it would be Databricks, at least in the open source optimizer. Another one that I'm interested in pursuing is doing rewriting with LLMs. So you can ask Claude or ChatGPT, whatever one of your favorite is, you say, hey, here's my SQL query, make it better, right? And it'll come back with SQL that's rewritten. And in some cases, if you do this with like Postgres queries, it'll actually run faster. There was a startup called EverSQL out of Israel that got bought a year ago, and they were basically using Claude to do this. Where you hey, optimize my query, and then they would go to the LLM and ask it to rewrite it. And they would give you explanations of why it got rewritten. The problem is, though, they didn't actually check anything. And I can give examples of this where you ask Claude for the query, hey, rewrite this. It gives you a SQL query back. It is faster, but it's actually semantically incorrect, meaning it can produce different results from the original query. See, the idea of this project would be you go to Claude or Llama, whatever your favorite LLM is, you rewrite the query, but then you take that query and then you basically do fuzzing on it. So you make a synthetic table or synthetic tables with fake data, and you run that query multiple times, the rewritten one, and see whether it produces the same result as the original query. And if not, then you reject it. So the idea is that we eventually want to have maybe a plugin system in opt-D where, as a rewrite pass, I can say call out to some LLM. And again, the idea would be producing the query in a better form for the query optimizer. The other thing I want to do is build a corpus or a library of all these different transformation rules so that we can sort of bootstrap the opt project. So the way things like Orca and Calcite and pretty much any query optimizer, the way they build out their transformation libraries is that they give the optimizer to customers. Customers complain about my query didn't get optimized well, and then they go add the optimization rules to fix those problems. So the problem for us is we're not a company. Nobody's using opt right now. So how do we get these rules? So I'd be interested in seeing if there's a way to take the open source query optimizers, the Cascades ones. So there's the Cockroach DB, Calcite, Orca. I don't know what's there in the Databricks one, but find other Cascades implementations, and could we define a universal language, a lingua franca, that we could then translate like the Cockroach DB transformation rules into this unified language, and then we could take that unified language and then convert that into opt rules. So now anybody building a new query optimizer could have this library of 1,000 transformation rules all ready to go. They just plug into their existing system instead of trying to bootstrap everything from scratch. WAN is interested in this for research purposes, but we are interested in trying to play around in Postgres with its query optimizer to inject statistics into it to force it to do things that it otherwise wouldn't do. So the idea is like, can you extract out the statistics that Postgres generates from analyze, and then can you then use like an extension and load that back in to override certain things based on when you actually ran the query, what are the results you're actually seeing? Another problem, or another big important problem of all this is like, how do you actually test and benchmark query optimizers? And benchmarking could just be not only how fast it is, or how fast can I generate a query with so many tables in it, but what's the quality of those query plans as well? We'll see this again later when we talk about Orca, because they care about this a lot because they're trying to run this in production. Any query optimizer would care about this, but Orca actually explicitly calls it out, where they have they have this testing framework called Taco with a Q, where they take like the best query plan and the second best query plan and actually run them for real and see whether the execution time actually matches up with what the relative cost differences were, right? And so start building automated infrastructure to evaluate these things, and then not just taking like TPCH queries, but could we sort of build like a fuzzer or use an LLM to generate a bunch of random queries and build a benchmark suite to test these things out? Or another one could be, how do my query optimizer can support SQL 92 queries. Okay, well, can I use an LM or something to generate something from the SQL spec, which we have, all the queries you would, all those different keywords and patterns you would have for SQL 92, and then verify your query optimizer can handle that. And then go to SQL 99, go to the next one, right, or 2003, and start building automated infrastructure for that. Another important thing we want to be able to do is, using opt, we want to be able to take the physical plans that opt generates and run it somewhere. So in the initial version, we're supporting data fusion, but eventually we want to be able to support Postgres. So you can imagine like a web interface somebody comes to that's at CMU, where people copy and paste their crappy Postgres queries in, opt runs on our side, then we come back with them like, here's the better version of the query. The problem is if you do SQL to SQL translation, like if you take the SQL input and then produce the SQL output, you may lose actually what all the knowledge, the information that the optimizer generated of what the true physical plan should be. So what you really want to be able to do is take the physical plan from opt, convert it, deparse it, or convert it back into SQL, but then inline plan hits to force join orders, to force index scans versus sequential scans. And there's a extension in Postgres called PG hint plan. So the idea is not just generating SQL from a physical plan, but also embedding inside of it the opt decisions. And the last project would be we're interested in better ways to represent what a predicate is for machine learning purposes. Like right now, there are basic techniques that can generate an embedding just for conjunctions and like simple greater than, less than queries. But we're interested in can you do more complicated, can you build a transformer to build a more complicated embedding that can handle disjunctions, in clauses, subqueries, like more complicated things you need to do to predict the potential cost of a query. And like I said, I'm running these very quickly. I'm happy to discuss any of them during office hours, or I'll be around also on spring break as well, if you want to go in more detail about what I mean for these different topics. So the way to get started is I'll post this on Piazza tonight. On the administration spreadsheet, there'll be a page where you have your sign up for your group of 3 members and what your project topic is. And then if you don't have any friends, for whatever reason, like, and you can't find a group, there'll be like a list saying I'm a free agent, and then we can figure out how to match you up. So the plan is you should form a team now, and then try to meet up with your team and discuss potential topics now, and then come up with a rough schedule what you're actually going to implement, and then that'll put you in place to present it on the 10th after spring break. Okay? Any questions or comments about project 2? Again, my list is not exhaustive. If there's other things you want to do, by all means, let me know. It's a special topics course. Everyone's going to have a good time.
Look good up brown. Matter of fact, hold this up. This is like that wood grain type of shit. Shout out to Blockhouse, my dogs. Catch one, Big Al, Mike Stroke, Gumby, all the dynamites. I'm not the one who be amping up the weak ass rhymes. If you spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as the thug from the gutter. Shit, some niggas claiming that the rapping is something. Don't push